All right. So yeah, this is just the definition of box topology, where you consider the sets of this form, products of this form, where each U alpha is an open subset of X alpha, and we claim that such a collection is a basis for a topology. Uh, of course, so claim is a basis for a topology on the product. Okay, we have to check several things. Well, actually, not several. First, we have to check that every point belongs to one of them. Well, of course, it is. So if x, let's say x alpha, is in the is an element here, then uh, then uh, then since this product is already an element of B, because each X alpha is open in X alpha, therefore this product belongs to this collection. We are done with the first condition for B to be a base for a topology, right? The first condition is that every point should belong to one element of the basis, right? So that's the first condition. The second one, if we have two such elements, and if we have a point in the intersection, then we should be able to find a third element containing that point, which is contained in the intersection. So, okay, let X be an element of such elements. This one, and let's say another one. Okay, so two such elements. These are basis elements, and I take an element in the intersection. But then look at this. What is the intersection of these? Uh, it is just şey doğru mu? A çarpı B ile C çarpı D'nin intersection'ı. Tabii burada bir eleman varsa hem bunun içinde hem bunun içinde. Dolayısıyla bu A çarpı C'nin içinde. Hem burada hem burada. Yok. A intersection C'nin içinde çarpı B çarpı D'nin içinde. Yeah, this is true. Right? So then X, which is X alpha, okay. However, ya da şöyle diyeyim. Then let third basis element W to be the intersection of these two. And what is this? This is nothing but this gadgets. And this is also an element of B, because this is open, therefore this is open in X. Since this is open in X alpha. Okay, so we have what? We have X is in this W, which is a basis element, and this is contained in this product. Actually, it is equal to, contained in this intersection. Actually, it is equal to the intersection, but it is also contained in the intersection, of course. So this finishes the proof that this collection is a basis for a topology. Well, this looks like a nice topology, and it is kind of a direct generalization of the topology on this Cartesian product. What was the basis for this? Well, it were exactly this kind of stuff, right? You take an open set from X, you take an open set from Y, and you take their products. They were the basis. And we just used this definition and generalized it to arbitrary products, right? We took open set from each space and we take their products. As the example below shows, this topology is way too strong. Okay, let's see some examples. Okay, example. Now, okay, let me choose my index set to be the set of integers, and for each n, let's say x is r standard. So here, this is in J, and consider uh, the uh, consider the product. So product of these n in n. So what is this? This is just infinitely countable product of standard topology on R. Okay, with box topology. Box topology. Well, consider the following function. Then the function, let's say f from where? From our standard into this product. Okay, into this product, our standard, given by this rule. So for each coordinate, I take t. Okay. Well, each of the coordinates are continuous functions, right? It is the identity function, t goes to t. So each coordinate function is continuous. However, this function is not continuous, okay? Is not continuous. Although, even though each coordinate function, coordinate of f of t is continuous. Not just continuous, they are the identity functions from R to R, but when I put them all together, this function becomes not continuous. Why is that? Well, let's take an open set in the product and check whether its inverse image is continuous or not. Okay, let U to be this product. 1 over n, no, sorry, minus 1 over n, 1 over n, n from okay, ben şey diye alayım, birden sonsuza kadar. So n is the set of integers from 1 to infinity, positive integers. Okay. Consider this set which is open in the box topology. Why is that? Because each of these are open in our standard, therefore their product is open in the box topology, right? If each piece is open, then the product is open. What about its inverse image? Well, so this is the set of all real numbers so that f of t is in U. But what is U? U is just the product. Okay, şöyle yazayım. Let me write this more explicitly. What is f of t? F of t is this t, right? T. And this should be inside U. What is U? U is this. Minus 1, 1, cross minus 1 over 2, 1 over 2, cross, right, goes like this. Minus 1 over n, 1 over n, and so on. So what is this then? Well, this is the set of all real numbers so that first coordinate is here, right? Second coordinate is here. Third coordinate is in minus 1 over 3, 1 over 3, and so on. And this goes till infinity. But what is this? T is less than in 1 in absolute value. T is less than 1 over 2 in absolute value. T is less than 1 over n in absolute value, right? This is just the same thing as this one, 1 over n, and from 1, 2, and so on. What is the real number which is less than all 1 over n's? That's only 0. So this set is only 0. Okay, consists of 0. And this set is not open in our standard. Okay, therefore this function is not continuous. So although this topology, box topology, looks okay at first sight, even such a function, which sends t to t comma t and so on, is not continuous. The reason is that this topology has too many open sets. Therefore, it is too strong. An open set of this type causes problems. So, for a reasonable topology on the product space, we should avoid such, sorry, not this, but such products. Products of arbitrary open sets. Okay. So to obtain a reasonable topology on the product set, on the product, we need to choose a topology, a coarser topology, avoiding arbitrary products of open sets. Like this one, right? Here in the box topology, we take arbitrary products, right? We take arbitrary products like this, and they cause a problem. So instead, we do the following. We take another generalization of the product topology on the product of two spaces. Uh, recall that the product topology, the product topology on x cross y had a sub-basis consisting of uh, elements of the form. Neydi bunun bir sub-basis'i? Şöyle şeylerdi. Pi1 inverse image of u. Bu da u cross y'dı. And pi2 inverse image of v. Bu da x cross v'di. Right? So this wasn't a basis. This was a sub-basis. And taking finite intersections of these elements, one obtains a basis for the product topology. What we will do, we will just generalize this definition, okay, of the product topology. Okay, so here is the definition. Okay, let okay, x alpha in J be a product of spaces, okay, product of sets where each x alpha is a topological space. Let pi alpha denote the projection map. Nasıl tarif ediliyor? Given by pi alfa'nın bir tane elemandaki değeri nedir? Şöyle diyeyim, pi beta diyeyim. Alfa diyelim. Bu notasyon tabii sakıncalı. Şöyle demem lazım. Okay. Because alpha is an index here, so I cannot use it here. Okay, so this is defined as follows. Whenever I have an element here, so it's a element of this type, I pick up its beta coordinate, okay? Okay. Then, okay, the topology generated by the sub-basis. Hangi sub-basis? Şuna bakacağız. Pi alpha inverse of u alphas, okay, where u alpha is an open subset, open, for each alpha is called the product topology on this product. Okay. So my sub-bases are the inverse images of open sets under the projection maps. Okay. So what's the basis then? Mark. So my sub-basis is this. Inverse images of S alphas, sorry, inverse images of U alphas, right? Alpha is an index set and U alpha is an open set. So this is my sub-basis. For this to be a sub-basis, what was the condition? The union of these elements should cover everything. Well, of course, just take this gadget. This is just the product of all of them, right? So it covers everything. So this is clearly a sub-basis. But what about the basis corresponding to this one? So the basis generated by this sub-basis is what? Something like this. It is finite intersections of such objects, right? Ya da şöyle diyeyim. Okay, şöyle diyeyim. What is this element? Well, this is nothing but the following. For any, maybe I should say beta. What is this? This is the product of some V alphas such that V beta, when it comes to beta coordinate, this is nothing but U beta, and all the rest is the whole space X beta. If yeah, I should say alpha, if alpha is different than beta. So what is this? This is like, in parentheses, let me write, this is like, X alpha. So we have products of X alphas, X alpha 1, alpha 2, something like this. But when it comes to beta coordinate, instead of X alpha, I have U beta, and then again the whole space is, right? So I take the whole topological space. Only at the beta coordinate I take U beta. Okay, and these gadgets are my sub-basis elements. What about the basis elements? Basis elements are intersections of these, right? Intersections of these. Let me explain this on an example, because for an arbitrary index set, it is difficult to represent these objects. Let's, for example, take J to be n, 1, 2, 3, and so on. Okay. And each x n to be again R standard, for example. So what's the basis for this? Sub basis consists of the following. So pi n is the product from this, right, from 1 to infinity into our standard, taking xn into ya da şöyle diyeyim, şuna pi m diyeyim, taking this element, this sequence, right? Elements of these are just sequences because they are functions from index set into the spaces. Here all these spaces are the same, so I just take I just consider sequences in R, and the mth coordinate is what? Mth coordinate function takes a sequence and sends it to its mth coordinate. Okay. Okay. Well, what is the inverse image of an interval? So pi m inverse image of, let's say, some interval, open set. Let me say something like this, AB. What is this? Well, it is R cross R cross R, and then here comes AB, and then R, and goes like this. Okay. Here, this is the mth coordinate. So these are the sub-basis elements. Sub-basis elements. All of the spaces are the whole space. One of them is an arbitrary open set. Okay, like this one. What about basis elements? Basis elements. Basis elements are finite intersections of such objects, right? These are finite intersections of what? Sub-basis elements. So they have the following form then. If you take, such products, finitely many of them, and intersect, you would get something like this. Some R, and then you have some A1 comma B1, and then maybe some other copies of R, and then you have A2 comma B2, right? And then again some copies of R, and so on. And finally you will have something like this, AN, BN. Okay, but after some point on, there will be only R's. Okay, only finitely many open set different than the whole space is allowed to appear in this product. Okay, so these are the basis elements. Well, clearly note that as a remark, clearly each projection function pi beta from this product into x beta is continuous, because I just my sub-basis elements are nothing but inverse images of the open sets here, right? I take an open set here in x beta, look at its inverse image. Those elements are my sub-basis elements, and therefore they are elements of the basis, and therefore they are elements of the topology. So these functions are clearly continuous. Moreover, you know, I took all the open sets here, right? Uh, Therefore, that topology is the smallest topology that makes this function continuous, because I looked at all the open sets here and uh, declared their pre-images as open sets, right? Therefore, this is the uh, uh, yeah, this is the smallest topology. Okay. Indeed, the product topology on this on this set is the uh, weakest topology uh, on this product, so that each uh, pi beta is continuous. These projection maps are continuous on the box topology also. So if I put here the box topology, this map is again continuous. But box topology is, of course, much stronger than this one, right? Here in this topology, I consider open sets only of this type, basis elements of this type. But in the uh, box topology, all of these copies of R can be replaced by arbitrary open sets. Therefore, you have just too many open sets. So box topology is much stronger than this product topology. Okay. Yeah, so maybe as a remark also, uh, if J is an infinite set, then the box topology is stronger than uh, okay, than the product topology. Why is that? Uh, because you see, well, of course, I should say maybe, because if you choose X alphas to be very small topologies, then they might be equal to each other, maybe. Yeah. If you take each X alpha to be the indiscrete topology, then the two topologies agrees. But usually this is more stronger uh, because okay, so for example, for instance, if uh, for any alpha in J there is some open set, let's say U alpha different than X alpha, then the product Product. Şu product'a bakalım. This is open in the box topology, but it is not open in the product topology, right? Because in the product topology, we allow only finitely many factors to be different than x alpha. But here, there are just infinitely many such factors. Therefore, a product like this is not open in the product topology. Okay. Convention is this. Unless stated otherwise, if I consider products of topological spaces, I consider the product topology on it. Okay. Unless stated otherwise, a product of topological spaces is considered with its product topology. Okay, not box topology. If I want to consider box topology, then I say so. Okay, I say that on this product of spaces, consider the box topology, or maybe some other topology. Okay, if I don't specify any topology, I consider the product topology. Okay. Okay, we have some results which combines product topology with the other notions we have seen so far, such as subspaces, being Hausdorff, and so on. One of them is the following. So let A alpha be a subspace of X alpha for each alpha in some index set J. Then this product, right, since each A alpha is a topological space by itself, this product has the product topology. Okay. Okay, is a subspace of this product if both products are given the box topology or product topology. So what we mean is the following. We may consider either box topology or product topology on this product. First, let's consider, for example, box topology. So what I mean is this. Both products, this product and this one are considered with the box topology. And what I claim is that with if this has the box topology and this has the box topology, then this thing is a subspace of this. Okay, it is not clear, right, why this is a subspace of this, even though each component is a subspace of X alpha, right? Even if each A alpha is a subspace of X alpha, it is not clear. Maybe it is clear, but it is not immediate that this thing is a subspace of this. But of course it is. So what we will do must show this thing is a subspace of this. Well, why is that? Okay, so okay, I guess it is easy to work with basis elements. Yeah. Okay. Şöyle yapayım. Okay. Subspace. All right. Maybe let me give a break and do this next time. Till then, I have to decide whether should I use it basis or not. Well, in any case, it's not something difficult, but it takes time, I guess. We will do this, and then we'll prove the same thing for product topology, where both of them have the product topology. Okay, but let me just stop here for today. Okay.